This is part one of a series of lectures from section 5.3 from Math 311, the course in linear algebra at Western Illinois University. Okay, so we have already looked at the wonderful things we can do if a subspace or a vector or Rn or any subspace has an orthogonal basis. Now the question is, how do we produce an orthogonal basis? Why are we guaranteed an orthogonal basis? So that's going to be the topic of this section, and we're also going to look at one direct consequence. So the process of creating an orthogonal basis from a regular basis is called the Gram-Schmidt process, and then a very nice consequence of that is something called QR factorization of certain matrices. So we'll look at both of those. So the main goal is and throughout this lecture, we're going to assume that W is a subspace of Rn, and we want to show that W has an orthogonal basis. And before we get started, we want to look at, remind you of a couple things. This was from the last section, section 5.2. If we do have an orthogonal basis, and we take an arbitrary vector v in Rn, then we can always write v as the sum of something in W plus something in W perp, the orthogonal complement. And what we did is we had to define this projection of v onto the subspace W, which is really a generalization of just projecting one vector onto another vector using this formula involving these dot products here, right? Then we also showed that if we define the projection as this vector, then we can define this thing called perp v, which is just the difference v minus the projection of v into W. That we showed last time, that's going to be orthogonal to everything in W, so it's in W perp, right? So we can basically also represent this as v minus this linear combination, and oops, there should be a UK right here, so shame on me. All right, so then, so this, we already knew this. Also, I want to mention that if we have any basis of a subspace, that we can replace any of these vectors in the spaces with a non-zero scalar multiple of it, and that it's still a basis. And hopefully we can see that's basically, you can do this. It's not hard to see why that is. It's basically, when you write things as linear combinations, you can just multiply and divide by some non-zero number. That's what it amounts to. And also, if it turns out that this is orthogonal, then doing this replacement will also you'll still have an orthogonal basis after that. So the reason I bring this up is because we go into, a lot of times we'll be doing some calculations where we'll get some fractions in our vectors, and we can always replace a fraction with whole number. We can replace, if we don't like that, if it's not pleasing to look at, we can replace it with a vector which is all whole numbers. All right. So this is if we want to, before I get to the actual process, I want to just look at a couple of scenarios here. So let's look in the two-dimensional case, all right? So let's suppose that W is a two-dimensional subspace, and let's say that x1 and x2 is a basis of W. Okay. So we can look at, say, here is x1, and here's x2. And we know that we can project x2 onto x1, and we'll get, well, the projection will be this, and then then x2 minus the projection will be this vector right here. And we can see this is certainly orthogonal to x1. Okay, so we can see that in fact, we know what this is going to be. This is x2 minus the projection of x2 onto x1. Okay, and we know that this is just going to be x2 minus the dot product x2 dot x1 or x1 dot x1 times x1. Okay. All right, now I'm going to show, what I want to do is we're going to show that our orthogonal basis is going to be x1 and this vector. And I'm just going to recall this, we're going to relabel this. We're going to let u1 just be x1, and we're going to let this vector be u2. All right. And then we can clearly see that u1 and u2 are orthogonal. All right. Now, that's not the hard part. The hard part is making sure that this is a that the span the span of these vectors is equal to the span of these two vectors, right? So let's see how we would do that. So let's take a linear combination of u1 and u2 first of all. So let's say a1 u1 plus a2 u2. All right, so we know that this, we want to show that this is a linear combination of x1 and x2. Well, this will be a1, well, u1 is just x1, and a2, or u2, is this. This is going to be x2 minus some number. We can call this lambda. So this will be x2 minus lambda x1, right? And we can clearly see that this is going to be a linear I can distribute and simplify, but this will be a linear combination of x1 and x2. So that's it. This is definitely in the span of x1 and x2. All right. Now let's take an arbitrary linear combination of x1 and x2. Let's call it b1 x1 and b2 x2. Once again, we can replace x1 with u1. And b2, well, from here we see that u2 is x2 minus lambda x1, but x1, remember, is u1, so we have that. So x2 can be written as u2 plus lambda u1. So okay, and so this is going to be a linear combination of u1 and u2. Okay, so we've shown that everything in here is contained in here, and everything in here is contained in here, so these have to be equal. Okay, okay, and that shows that, so that shows that u1 and u2 will be a basis, will be an orthogonal basis of W. Okay, so just maybe as a very quick example of how this would work, let's say that we had the vectors 1, 5, 3 and 201. Okay, let's say that this, so let's say this is x1 and this is x2. All right, so we let u1 be just 1, 5, 3, and u2 will be 2, 0, 1, minus the dot product of this and x2. So this would be 2, 0, 1 dot 1, 5, 3 over 1, 5, 3 dot 1, 5, 3 times 1, 5, 3. And this, if we do the dot calculation, this is going to be 5, and this dot product, this will be 1 plus 25 plus 9. So if my arithmetic is correct, that should be 35. Okay. So this is just going to be 201 minus 1/7 times 153. Okay, and if we do some arithmetic here, this is 2 minus 1/7, 0 minus 5/7, and 1 minus 3/7. So this is going to be, this is 14/7 minus 1, so that will be 13/7, negative 5/7, and 4/7, because it's 7/7 minus 3 is 4/7. Okay, and now we could leave this, we could use this as our U2 if we wanted to, but again, if we don't like fractions, we can just replace it with multiply this by 7 and get 13, negative 5, and 4. And we can see, hopefully, that these are going to be orthogonal. 1 times 13 plus 12 minus 25 is 0. So these are orthogonal, and more importantly, they're going to have the same span because of how U2 is defined. So this is an orthogonal basis. In this case, all right. Once again, if you wanted to keep this vector in here, that's fine. Okay, but you can always replace this with a scalar multiple of that. So that's how you would do it if you had a two-dimensional subspace. Now, what about a three-dimensional subspace? Okay, so now in this case, say we had x1, x2, and x3 is now a basis of W. All right, now the way we do this is we're going to first focus on these two vectors, x1 and x2, okay? And we look at just the span of those, and that's a subspace. And we know that we can find an orthogonal basis for that subspace. So let's say let's say this plane represents the span of x1 and x2. Okay. Well, and from what we just did, we can replace x1 and x2 with an orthogonal basis. So there's going to be some vectors u1 and u2 that will act as an orthogonal basis of this. So this is going to be equal to the span of u1, u2, where these are orthogonal, based on what we just did in the previous example. And then we can take x3. If x3 is this vector here, then we can again calculate the projection of x3 into this new subspace, and then we can also find the difference perpendicular to that. So we can take this vector then. This vector will be our u3. This is obviously orthogonal to both of these vectors, and we'll see that we're going to see that they generate the same space. So we'll let this vector be u3, which will be x3 minus the projection of x3 into this. We'll call this new subspace w2, where we say that this subspace right here, and this is going to be a linear combination of u1 and u2. Right. So to show you why this would work, if we take an arbitrary linear combination of the u's, let's say u1 plus a2 u2 plus a3 u3. Okay, so this will be a1 u1 plus a2 u2 plus a3 times u3, which is x3 minus the projection of w2 of x3 into the subspace w2. Now these two, this is in the span of u1 and u2, but we know that this is also equal to the span of x1 and x2. Okay. And then this is clearly this is x3 minus, again, something in the span of u1 u2, but this is equal to the span of x1 and x2. Okay, so you have something in this span plus something times x3 plus something in the span of x1 and x2. So this is in the span of x1, x2, and x3. Okay, all right. So we get that the span. So we get that the span of u1, u2, and u3 is contained in the span of x1, x2, and x3. Okay. And then similarly, what we can do is we can do, I'll let you maybe do the other part, take a linear combination of x1 and x2 and x3 and show that they're linear combinations of u1, u2, and u3. The argument is very similar. Okay. And then these, we show that these are actually equal. All right, so that is I think you get the idea here, that we can basically, you know, we can build this in steps. We can just go back to, then if we want to do this with a four-dimensional subspace, we take a basis with 4 vectors, and we just take the first 3 vectors, do this process on that, and take the subspace generated by the first 3 vectors, and then project the 4th vector onto that new subspace, and take the vector that's perpendicular to that, and that would be our that would be the 4th vector in the orthogonal basis. So that is how we get this next result, the Gram-Schmidt process, which says that if this is a base, if x1 through xk is a basis of W, we can just go through these calculations, and that's how we get an orthogonal base. Well, that's not only do we get an orthogonal basis of W, we get an orthogonal basis of all these intermediate subspaces here. So u1 is just x1, the original vector. Then u2 is x2 minus the projection of x2 into the span of u1. u3 would be x3 minus the projection of x3 into the subspace generated by u1 and u2, and so on. Okay, so yeah, that's what's really going on here. At each step, that ui is just xi minus the projection of xi into this intermediate subspace of ui minus 1, where ui minus wui minus 1 is the span of u1 through uk minus 1, or I minus 1 in this case. Okay, so do the calculations, and notice that now what's even more important here is that at each step, this intermediate, this wi, the span of the x1 through xi is equal to the spans of u1 through ui's for each I, and that this is going to be an orthogonal basis of this subspace, and in particular, the u1 through uk will be an orthogonal basis for w. Okay, so that's the Gram-Schmidt process. And so the good news is it works. The bad news is the calculations can be a little messy, and there's a lot of arithmetic. So we're going to work through a specific example in the next video.